Good day, everyone. Today, we will be discussing the limiting and excess reactants. So, the objective of this report is at the end of the lesson, the learner should be able to distinguish limiting reactant from excess reactants in a chemical reaction. Second, show the use of the limiting reactant in a stoichiometric calculations. And third, calculate limiting and excess reaction in a chemical reaction. But before that, let us play a game titled Guess the Word. I will show you some picture. The correct answer will be shown in the last part of this video. So, limiting reactant or limiting reagent is a substance in a chemical reaction that determines the amount of product formed. Reactions follow the mole ratio specified in a balanced chemical equation, which is why a limiting reactant exists. Reactions follow the mole ratio in balanced equation. For example, 1.1 means 1 mole of each reactant is needed. The reactant with less quantity runs out first and is the limiting reactant, while other is in excess. An example reaction shown is 2C6H6 plus 15O2 to 12CO2 plus 6H2O. With calculation comparing limiting and excess reactants for different amount of benzene 6H6. When chemicals are mixed to undergo a reaction, there are often mixed and stoichiometric quantities. That is, in exactly the correct amount so that all reactants run out at the same time. To clarify this concept, let's consider the production of hydrogen for use in the manufacture of ammonia by the Haber process.
The Haber process, also called the Haber-Bosch process, is an artificial nitrogen fixation process and is the main industrial procedure for the production of ammonia today. The process, also known as the Haber-Bosch process, is an artificial method for fixing nitrogen. It is currently the primary industrial procedure used worldwide for the production of ammonia. Ammonia, a very important fertilizer itself and a starting material for other fertilizers, is made by combining nitrogen from the air with hydrogen according to the equation N2G plus 3H2G equals 2NH3G. Ammonia is a vital fertilizer itself and serves as a starting material for producing other types of fertilizers. From the balanced equation, we know that each N2 molecule requires 3 H2 molecules for the reaction to occur. The balanced chemical equation N2 plus NH2 equals 2NH3 tells us that one nitrogen molecule N2 needs 3 hydrogen molecules H2 to react. This means the reaction will only work properly if there are 3 H2 molecules for every one N2 molecule. Thus, the required H2 N2 ratio is 3H2 1H2. There is not enough hydrogen to react with all the nitrogen. That is, the hydrogen will run out first, leaving some unreacted N2 molecules. The necessary ratio for the reaction between hydrogen and nitrogen is 3H2 1N2. This is the ratio derived from the balanced chemical equation.
Good day everyone, in here we have a problem. We have aluminum and sulfur. We know their masses 5 grams of aluminum and 25 grams of sulfur. Our task is to find two things. First, how many grams of aluminum sulfide will be produced when they react, and second, how much of the extra reactant will be left over. Before we solve anything, we must write and balance the chemical equation. This page shows the balance reaction. Balancing is important because it tells us the correct ratio in which the substances react. Here the equation tells us that 2 moles of aluminum react with 3 moles of sulfur to form aluminum sulfide. We in numbers in front of the formulas to make sure both sides have the same number of atoms. Here we learn that aluminum is the limiting reactant because 5 grams of aluminum makes less than 25 grams of sulfur. This means the amount of aluminum we have limits how much aluminum sulfide we can make. This section shows how to convert the mass of sulfur into the number of moles of sulfur using its molar mass. The given mass of sulfur is 25 grams and the molar mass of sulfur is 32 grams per mole. By dividing the mass by the molar mass, the calculation determines that there are 0.780 moles of sulfur present. Now, we start the actual computation. The page shows how to convert the 5 grams of aluminum into moles. We do this by dividing its mass by its molar mass. 5 grams divided by 27 grams moles equals 0.185 moles. This step is important because chemical reactions happen in moles, not grams. By finding the moles of aluminum, we can later compare it to the moles of sulfur and figure out which one will run out first. Let's use the calculated moles of sulfur and the balanced chemical equation to find the maximum amount of aluminum sulfide that can be produced from only the sulfur. This calculation, when compared to the amount of product formed from aluminum 0.93 moles in section 20, helps identify the limiting reactant, the reactant that produces the lesser amount of product is the limiting one. In this step, we identify the molar mass of each element. Aluminum has a molar mass of 27 grams and sulfur has 32 grams. We get these values from the periodic table. Molar mass is important because it allows us to convert grams, which is the given unit, into moles, which is the unit used in chemical reactions. So, this page simply prepares us to the calculations by giving the needed molar masses. Lastly, we calculate the mass of aluminum sulfide formed. We use the moles of aluminum sulfide produced by the limiting reactant, which is 0.095 mole, and multiply by the molar mass of aluminum sulfide to find that 13.9 grams of aluminum sulfide is formed.
This step calculate how much sulfur actually reacted with the limiting reactant of aluminum. Using the mole ratio from the balance equation, 2 aluminum plus 3 sulfur to aluminum 2 and sulfur 3, which is 3 moles sulfur per 2 moles of aluminum. with 0.185 moles of aluminum, the moles of sulfur that reacted are 0.185 moles of aluminum times 3 moles of sulfur over 2 moles of aluminum equals 0.278 moles of sulfur. Find the unreacted moles of sulfur, then subtract the reacted moles from the total available. So 0.780 minus 0.278 equals 0.502 mole of excess sulfur. Then, convert moles to mass using sulfur molar mass. 32.0 grams of moles times 32.0 over 1 mole equals to 16.1 of excess sulfur. Balance equation. 6C H1206 plus 6O2 to 6CO2 plus 6H2O. 1 mole of sucrose produces 6 moles of CO2. Moles of CO2 calculation is 0.5 moles of sucrose times 6 equals 3 moles of CO2. Then, the molar mass of CO2 is 12 moles plus 2 times 0, which is 16 moles equals 44 moles. Then last one, the mass of CO2. 3 moles times 44 grams or moles equals 132 grams. Given 0.5 molecules glucose, 6CH12O6, use the 1.6 mole ratio with CO2 to get 3 mole of CO2. Then multiply by CO2's molar mass of 44 grams of mole to find mass equals 132 grams of 6O2. This is about figuring out how much carbon dioxide comes from glucose. So, the rule is 1 part of glucose makes 6 parts of CO2. If we have a half part of glucose, multiply by 6, we got 3 parts of CO2. From 0.5 moles of glucose, 3 moles of CO2 are produced using CO2 sulfur molar mass of 44.0.1 mole. Its mass is 3 times 44.01 equals 132.03 grams. 3 moles of CO2 is 44.1 grams per mole. So, multiply it by 3 by molar mass. The mass is 44.1 grams. So, 132.03 grams of 2. Finding out how much CO2 forms when 25 grams of glucose reacts with 40 grams of oxygen. We need to find which reactants run out first that we call limiting reactant. Then, use that to calculate the mass of CO2 made using the reaction ratio of 1 glucose makes 6 CO2.
When approaching this problem, observe that every 1 mole of glucose requires 6 moles of oxygen to obtain 6 moles of carbon dioxide and 6 moles of water. Step 1. Determine the balanced chemical equation or chemical reaction. The balanced chemical equation is already given. So the calculation shows that the exact amount of oxygen requires to react with all of the available of glucose. Since there is more than enough oxygen, the amount of glucose is used to determine the final amount of product made. Step 2. Convert all the given information into moles, most likely through the use of molar mass as a conversion factor. The image illustrates calculating the number of the moles for a given mass of a substance by dividing the mass by its molar mass. Step 3. Calculate the mole ratio from the given information compared to calculated ratio to actual ratio. If all of the 1.25 moles of oxygen were to be used up, there will be 1.25 times 1 over 6 or 0.208 moles of glucose needed. There are only 0.40 moles of glucose available, which makes it limiting reactant. The calculation determined that 0.208 moles of glucose will be required to use all of the available oxygen, since only 0.40 moles of glucose are actually present. The glucose runs out first those limit of amount of product that can be formed. If all of the 0.40 moles of glucose were used up, there will be need to be 0.1328 times 6 or 0.8328 moles of oxygen needed, because there is an excess of oxygen. The glucose amount is used to calculate the amount of the product in the reaction. The text identifies the limiting reactant in the chemical reaction by calculating how much of one reactant is needed to fully consume the other. Because there is an excess oxygen of glucose is the limiting reactant. The amount of the limiting reactant is what the if more than 6 moles of oxygen are available per mole of oxygen, hydrogen, and carbon dioxide, hydrogen, and oxygen, the oxygen is the excess glucose is the limiting reactant. If less than 6 moles of oxygen are available per mole of glucose, oxygen is the limiting reactant. The ratio is 6 mole oxygen per 1 mole glucose, or 1 mole oxygen per 1.6 mole glucose. This means 6 mole oxygen and 1 mole to carbon dioxide, hydrogen, and oxygen. The recipe requires 6 to 1 ratio of oxygen to glucose. That ingredients you have less of is the limiting reactant. It stops the reaction. The ingredients you have more is the excess reactant. Some will be left over. Step 3. Calculate the mole ratio from the given information compared to calculated ratio to actual ratio. If all of the 1.25 moles of oxygen were to be used up, there will be 1.25 times 1 over 6 or 0.208 moles of glucose needed. There are only 0.40 moles of glucose available, which makes it limiting reactant. The calculation determined that 0.208 moles of glucose will be required to use all of the available oxygen, since only 0.40 moles of glucose are actually present. The glucose runs out first those limit of amount of product that can be formed. Step 4. Use the amount of limiting reactant to calculate the amount of carbon dioxide or hydrogen produced for carbon dioxide. The calculation shows in the image is incorrect. The correct mole ratio is carbon dioxide to glucose is 6 to 1, not 1 to 6. Step 5. If necessary, calculate how much is left in excess. 1.25 mole minus 0.84 mole equals 0.4172 moles of oxygen left over. In short, the calculation in the image shows that final step for finding the amount of excess reactants remain after the chemical reaction by subtracting the amount used from the initial amount.